Okay, so let me share. All right. So let us look at what is called product manifold. Product manifold. So question is, suppose M and N are smooth manifold manifolds of dimension M or yeah M and N respectively, then is M cross N the Cartesian product. Product is M cross N a manifold, a smooth manifold. Yeah. Any answer to this question? What do you think? Will it be a manifold? It will not be.
Yeah, it should be.
It should be a manifold, right? So, so what would be the guess for the dimension? What will be
Yes.
candidate for the dimension? Yes. Yeah, Dhruv, say that again.
Yeah, I'm thinking.
Okay, there are more questions even. So is this is one is M cross N house drop given M and N a house drop is M cross N second countable? Yeah, the answer is yes, yes. And here also yes. So, and this is an exercise from point set topology. Exercise from point set topology. All right. Now the most important thing is charts. So you have charts in M. So say let F, so which is U alpha comma phi alpha. Alpha is in some index set is an atlas on M, right? Of course, which lies in the differentiable structure. And F tilde, F tilde, which is V alpha comma psi alpha B so let me put it beta. Beta is in some index set is a is a is a is an atlas in N which lies in the differentiable in the maximal atlas. Right? So now can you give an atlas for M cross N? What would be a natural guess?
The product of Atlas. The Cartesian product of Atlas.
So Cartesian product of atlas. What is mean? So
That that's U alpha cross V beta and with homeomorphisms psi beta and psi alphas.
right. So you can cross. Sorry, you can look at such thing. So open set U alpha beta. What happened here? U alpha beta as U alpha cross V beta. This is open in M cross N, right? In the product topology. And the map phi alpha beta, this is phi alpha comma psi beta. This is map from U alpha cross V beta to some open subset phi of U alpha cross phi alpha Pu alpha psi beta of V beta, which lies in R n plus n, right? So x is in here, y is in here. So x comma y goes to p alpha x comma p beta y, right? This is the map, right? Now this is the map, so you can prove this is a so this I leave at as an exercise because there is nothing. So prove that p alpha beta is a homeomorphism. There is nothing here. And now next will be what will be whether this set this product so covers whole M cross N, right? So this since M is contained in union of alpha in the index set U alpha and N is contained in union of alpha, so maybe I should put a different index set for N. Yeah, prime. Lambda prime different index set V beta right. So M cross N will lie in union of alpha beta lies in this cross this U alpha cross V beta. Alright. Now this is nothing but alpha beta is in this. This is U alpha beta. Alright. So it covers the union of U alpha beta covers N cross N. Now the compatibility. Right. So let me go back and okay. So let me write F here, script F here. Did I F and F tilde I've written, so let's call it this. U alpha beta, P alpha beta, alpha beta. So this is alpha comma beta coming from this. Alright. So Glenn, F tilde is an atlas on M cross N. Alright. So this is what we were showing here. So phi alpha is a homeomorphism, that's an exercise, and it M cross N is covered by this union, is contained in the union U alpha beta. Alpha beta belongs from this corresponding index sets. And now compatibility, right? So compatibility means you have, let's say, the U alpha beta, P alpha beta, and U alpha prime beta prime, P alpha prime beta prime are suppose two charts, right? With non-empty, with U alpha beta intersection U alpha prime beta prime non-empty. So if it is empty, then it is trivially true, compatible. There's nothing here. But if the intersection is non-empty, then only one need to check. So how does it go? So U alpha beta intersection this is U alpha prime beta prime, right? So from here we have two charts. One is P alpha prime beta prime that is also taken to Rm plus n, and this is phi alpha beta. This is also taken in Rm plus n. Now we want to look at first this map, right? Which is P alpha prime beta prime compose P alpha beta. Now what is this map? Can you write it properly? What is this map? How does it look like? So what is this map? P alpha prime psi beta prime, right? And this maps to Rm cross Rn. And what is this map? P alpha comma psi beta, right? So here this is actually looking at this as Rm cross Rn, and this is also looking at Rm cross Rn. Now Rm maps to Rm here, and Rn, the part of Rn goes to Rn here, right? So what is this? So if you write it alpha, this is some p comma q, 2 point. So let me write it Yeah, yeah. So maybe in the next page. So P alpha beta compose alpha prime beta prime compose P alpha beta inverse. Let's call it P comma Q, 2 points coming from where? Rm cross Rn. The P is in phi alpha of U alpha, Q in phi beta of psi beta of V beta. Alright? So what is it? What will be this map? Phi alpha beta inverse?
Psi alpha inverse, comma, psi beta inverse.
Right. So phi alpha inverse P, comma, psi beta inverse Q. It's corresponding map, right? And here also, if you apply phi of alpha prime beta prime, so phi beta, phi alpha maps to the first component, phi alpha compose phi alpha, so phi alpha prime compose phi alpha inverse P, comma, phi psi beta prime beta prime compose psi beta inverse Q, right? Now we see this component. So what do we get? We get phi alpha prime beta prime compose phi alpha beta inverse is nothing but phi alpha prime compose phi alpha inverse, comma, psi beta prime compose psi beta inverse. Now each of the component are smooth, right? So phi alpha prime compose phi alpha inverse and psi beta prime compose psi beta inverse. Well, we don't need to go to smooth. Yeah, we need to go to smoothness. These are maps from open subsets of Rm and Rn to open subsets of Rn and Rn respectively. Right? Hence, are smooth maps. Hence, P alpha prime beta prime compose P alpha beta inverse is C infinity. Right? Each component is smooth. Hence, this is smooth. Yeah, from Rn to Rm or Rn to Rn, if you have a map, let's say f1 comma f2 comma fn, and this combination of this one, so tuple of f1 f2 fn, call this capital F. So you know already that capital F is C infinity if and only if each component is C infinity, right? This part you know from calculus, where it's a map from some open subset of Rn to some open subset of Rm to some open subset of Rn, and then it's happened. Hence we get C infinity. There is nothing here. Yeah, so compatibility is not a question. Just to write these things up properly, that's it. Any question here? Any question? Okay. Since there is no question, so let us look at some examples of a smooth map. So examples of smooth maps. Suppose M and N are smooth manifolds, then the projections pi 1 from M cross N to M and pi 2 from M cross N to N is RC infinity. All right, this is true for any manifold. So you already know from Rn to R. If you look at projection from Rn to R, the first component, second component, third component, each of them are smooth. You already know it, right? These are coordinate functions. So it is in general true for the product manifold. So for example, if you for instance, R3 R2 cross R3 to R3 x1 x2 comma y1 y2 y3 to y1 y2 y3, this is a smooth map. Of course, this example you already know, but the point is this is true for any general case where M and N are two smooth manifolds. Now, how do you prove such thing? Right? I need to give a proof. Yeah. So how do you prove it? So you look at a point P comma Q. So look at P comma Q belongs to M cross N. Right? So P is in M, Q is in N. So you look at the chart at P and chart at Q. Let U comma phi is a chart. So this is called U1 P1. Chart at P in M, and U2 comma phi2 is a chart. Well, chart lies in the maximal atlas of M and maximal atlas of N respectively. Chart at Q in N. Now, by previous observation, this U1 cross U2 and phi1, phi which is phi1 comma phi2, this is a chart at P comma Q in M cross N. All right. It's fine. Now this you have M cross N here, and you have N here. This projection, uh, whatever. This is first you take first one M, right? So in this case, we take this chart as open set as U1 cross U2. So here we look at phi, and here we look at phi1, right? Now here this is Rm cross Rn. Here it is Rm. Now we combine this. So what is it? Phi1 compose pi1 compose phi inverse. This is nothing but phi1 compose pi1 compose phi inverse is phi1 inverse comma phi2 inverse. All right. So what is it? Come on, say that. What is it?
Identity.
Right, right. So phi1 compose pi1 compose phi1, yeah, pi1 of, let's write it in this way, pi1 of phi1 inverse, phi2 inverse. This is nothing but phi1 of phi1 compose phi1 inverse, and this is identity. So which is identity on identity on yeah phi1 of
Sir, it's not identity, right? It should be like from higher dimensional, from m plus n, you're going into n. So it'll be the projection map in Rn plus n.
right. That's true. So this makes sense, but this is also fine. This is phi compose phi inverse is also fine, right? Because so if you put some point here, phi inverse, let's say x comma y, phi inverse x, phi 2 inverse y, we'll get y. So let me write in a better way. So this is fine. This would be actually the components of Rm only, right? So this is fine. So better to write is in this way. Phi1 of phi1 inverse x, phi2 inverse y. So xy belongs to uh, phi of u1 comma u2, u1 cross u2, right? So now this one is phi1 compose phi1 inverse. So phi1 of this same phi1 inverse x, and this is x, right? So the map is xy goes to x, right? So where is this xy lies? Phi of u1, phi1 of u1, phi2 of u2, and that goes to phi1 of u1. Does this make sense? Yeah?
Yes, sir.
Okay. So this is what is projection. Of course, if you write in this fashion, it will be a little difficult to understand. So identity where, right? That is a big question. Identity where. But this map is going from where to where. This is identity on phi1 of u1. So which is this is identity on phi1 of u1. All right. Any question here? So similarly, one can do prove the projection n is also smooth. So smooth and C infinity will use interchangeably. This will mean the same thing. Okay, so next look at another thing. So another example. So example 2. So suppose here this R goes to R maps to S1 by t goes to cos t comma sin t. Right? Is it a smooth map? Yeah, the question is it a smooth map?
Mm, Yes.
Yeah, right. So this you have taken already that I mean smooth map, no problem. But how to show? Well, if you
So
forget this, yes, yeah,
take the
Arshid?
atlas, that upper hemisphere, lower hemisphere, and then in the upper hemisphere we can look at the map which is going, which is C infinity.
So projections, right? Yep. So upper hemisphere, what is the chart map? What is the chart map?
It is going downwards to x-axis.
Right. So it is projection on first coordinate.
Yes, sir.
Yeah. So this, if you now forget about this one S1 and look at it and in R2, you know this is smooth, right? Yeah. So if you forget S1 and look at R2, this is smooth. You already know, right? This is this is just in calculus, right? From Rn to Rm, you know what is a smooth map. So if you forget S1 and look at it as a map in R2, it's already smooth. So it is of course going into S1, but one can think of this as map from T to R, I mean R to R2. But here, of course, as Harshit told, this one look at these charts. So look at this chart, and here, of course, fix a point here, and if it goes to upper hemisphere here, upper hemisphere, then it will be this projection map will be phi t equal to phi of xy, phi of xy equal to x, right? Similar things, and then you this is the map. Let's say f, and you compose, and here it is just identity, right? And you want to look at this map, which is smooth, simply map. Right? There is nothing to prove. So check yourself that this is smooth. All right. Now let's look at the analog to, of course, R goes to R2, this part. So yeah, maybe let me write that as an example also. So example 3, R goes to R2, fx equal to x comma 0 is a smooth map, right? Is this fine? Well, of course, you know this from calculus, but is it fine from the point of view of in our manifold setting? Right? You take chart map both side identity, right? Well, there is nothing. So it's already scene 3D map because you already know from calculus. Well, let's go to the analog of this one. So suppose M N1 and N2 are smooth manifolds. A map of dimension M N1 and N2. A map M to F from M to N1 cross N2 is infinity if and only if and only if. So Fp would be F1p lying in N1 and F2p lying in N2 if and only if F1 and F2 both are infinity. So this proof I'll give as exercise, the proof of this one exercise. And this is not a very difficult, simple exercise. Just routinely check. You just look at chart maps, in N1 cross N2, you already know now, and then compose it with the corresponding charts. So get habituated with the charts. That's it. All right. So next, so once you know this one, then one can see the following. So the following thing, what is this? So, so example 5. Suppose this is very simple. So yeah. So restriction. So this is actually restriction map. We'll prove the general later. Restriction map, restriction of a smooth map in R2 to S1 is a smooth map on S1. So first you look at, instead of smooth map, we just look a smooth function uh, going to R. So in R2 you have functions, right? You have smooth functions, you know it. Now restrict those smooth functions on sphere. we'll get smooth functions, right? So restrict those smooth functions to S1 circle. Similarly, if you look at smooth functions in R3, restrict it to sphere, unit sphere, and you will get smooth functions on sphere. You might not be able to get all the smooth functions this way. We did not say that yet. But what do you get? You get a collection of smooth functions, examples of smooth functions. So, for any kind of analysis, you need to know a lot of functions, such functions, right? Here we are actually giving this uh, the notion of smoothness in a different space than other than different spaces other than the Euclidean. So there we get the notion of smooth manifold, smooth structure and smooth maps, but we need to have enough examples. So first thing is that if you look at maps in Rn, restrict it to circle or the unit sphere on that, you get a smooth function again, right? Right. So any idea? Any question here? Hmm? Any question? Okay, let's see how to prove such things. So here it is. So you look at this map I from S1 to R2. This kind of notation is called inclusion. This is just the subset, right? It's R2. So XY in S1 goes to XY. Here's the identity map on S1. This is called inclusion map. Is the inclusion map, right? Now you know these are smooth, right? Because if you fix a chart here and the first component and second component both are smooth. Now this I is a smooth map. Check. Right? You need to have an atlas here, S1, and then compose here. In this case, the other side it's identity. Now look at each component, it is smooth. And then you look at the other component. This is again smooth. So by the previous exercise, you actually get the smooth map. I is a smooth map, right? Now the point is here. Now it is very easy. Now suppose if from R2 to R is infinity. Now this you look at I here S1. So this is a composition map, right? If compose I, this is also smooth map as it is the composition of two smooth maps. All right. Any question?
Sir, what is F?
F is any smooth function. If is suppose F is any smooth function is a C infinity function.
Okay, sir.
Right now, so this is F compose I is the restriction. So F compose I is the restriction of F on S1, right? This is the restriction map. So which is actually composition of two smooth map. Hence it is smooth. Right now you can think of that instead of S1, what kind of subset you can take and you still get the smooth function. Yeah, this is a very easy question, but very, very important as well. All right. Any question here? Now the final thing today is concept of local coordinates. So, like, I mean, in Rn, you have coordinates, right? Say R1, R2, Rn. Instead of x1, I wrote it R1, R2, Rn because x1, x2, xn will denote something else, right? So coordinates in R, we write as R1, R2, Rn. So these coordinates are there. So we want to define coordinates in the manifold locally, right? Now suppose M, so this is M, the smooth is infinity or smooth manifold. Suppose P is here, a point in M, P is in M, and suppose U is a chart. So this is U, and this is Phi. Going into Rn and on to Phi of U. It's open in Rn, right? Now the point is you look at shrink the neighborhood U so that you become U is connected. So shrink U so that U is connected. So this implies phi U is also connected, right? Now on phi U, this is open subset of Rn. You have coordinates. We have coordinates here on P of U, right? Say R1, R2, Rn, as in case of Rn, right? This is global coordinates. Now we define local coordinates x1, x2, xn on U such that xj is xj is what? Xj should be mapped from uj to r, right? U to r, right? Yeah, what should be quotient? Xj is equal to
Sir, for any point on U, we take its image in Rn,
yes,
and over there we look at the the xjth component.
right. That is true, but we need to write it in U only. So we need to pull back by phi, right? So we want this Rj compose yeah, maybe this one. Yes, yeah. Rj compose phi, right? Does this make sense? Yeah. So phi is from, as you said, this is in Rn. You just look at Rj, which maps to R. So this gives you a coordinate. So this xj, j from 1 to n, this is our coordinate system. This is our coordinate system, right? So whatever we want to define partial derivative with respect to xj, but remember xj is after going via chart map and then the jth component, jth coordinate. All right. So next time we'll say what is partial derivative with respect to xj and so on.